Okay, good afternoon, lads and ladies. Sorry, I'm running a few minutes behind. I had to sub for another teacher, and that class just ended. So today we're going to pick up where we left off last time. Just a second to get my shit organized here, and we can get moving. I have to remember what we're doing. So I believe last time we finished up section 5.4 talking about indefinite integrals and the net change theorem with a little warning that the place we were going after that was going to be kind of tough. And indeed, the place we are going is a little bit complicated. So today I want to get a start on section 5.5. But in order to do that, I need to go back and talk a little bit about something called a differential. So let's do this. Just to be clear, 5.5, this is the meat of today. The substitution rule, it'll be this section. But in order to talk about that, there's something that we need from back in, where was it again? Maybe it's 3.9? Yeah, differentials, which is more of a notation thing than anything else. This is where you learned about the linearization, and we talked about how to linearly approximate a function. But there's another piece in here that we didn't talk about back then, having to do with some kind of wonky looking notation. You may remember this stuff. So I'm going to go back and I'm going to cover that material, and you may have a problem or two from section 3.10 in your homework here, but there won't be anything where I actually ask you to use a differential to approximate, because one, that's wrong, like the textbook just gets it wrong, and second, we're really only here to talk about differentials. So most of what we're doing today comes from 5.5. It's just a little bit of notation we're going to go back and grab from section 3.10. So without further ado, today is the 23rd. All right. So today will be about differentials. Which are section 310, and substitution, which is 5.5. So first, what is a differential? That's a question that drove me nuts when I was in Calc 1. And so let me get that out of the way. If y equals f of x is a function, then the differential dy is defined to be dy equals f primed of x times dx. This isn't really a satisfying answer to the question, what is a differential? So for now, think of it as just a piece of notation, right? Where is this coming from? The usual notation, dy over dx equals f primed of x. And I'm going to put this in quote bunnies, saying I'm not really responsible for it, multiplying by dx, right? If you multiply both sides of this equation by the symbol dx, then you can cancel the dx's here, and you would get f primed of x dx on the right and just dy on the left. You get this. What is it really? Well, depends on who you ask. If you ask someone like me, whose background is primarily in differential geometry, when it comes to this sort of thing, at least, analysis, I look at it from a differential geometry perspective, I would say that this is what's called a one form, meaning it's a linear functional from a tangent bundle to the real numbers, which is not at all helpful for comprehending at this level. So what you guys should probably think about this as, dy is the infinitesimal change in y. This is the, let me find another color here that might stand out. This is the infinitely small change in y, and dx is the infinitely small change in x. So what dy equals f primed of x times dx is telling you is that if you're looking on the graph y equals f of x, and you make a teeny tiny little change in x, then you can expect a corresponding teeny tiny little change in y that you calculate by multiplying the teeny tiny change in x by the derivative at that x value. Okay, you put all of those things together, and that creates the differential dy. If you want the real answer to this, you're going to have to read the Wikipedia page for differential form, which is not an easy read, but this is what's called a one form, meaning it's a map that takes vectors to real numbers. It's a real valued map that takes in functions and spits out real numbers. For us, it's a necessary and important piece of notation to understand substitution. So before we get into any of the substitution, I just want to talk a little bit more, do some calculations of differentials. If y is equal to, say, x cubed minus 2x squared plus 3, then find the differential dy. Well, here's f of x, right? So dy should be f primed of x times dx. And f primed is 3x squared minus 4x. So you would put all that in parentheses and then slap on a dx, and that is dy. This is all, right? This is it. You just take the derivative and then multiply that whole thing in parentheses by dx, or whatever your inside variable is. If z is equal to the inverse tangent of x, then let's find dz. Well, again, here's f of x. So dz should be f primed of x times dx. F primed of x here is 1 over 1 plus x squared. That's the derivative of inverse tangent of x. So dz is that times dx. Okay? And you could read this as saying, if you want to find the little vertical change in the function f of x, you could take the little horizontal change in x and then multiply by this, and that would tell you about how much you go up. There is a meaningful connection here to linear approximation, but it's not worth even discussing in this notation because dz and dx are infinitesimal. They're not real numbers. They're smaller than any real numbers. The reason I'm showing you this is so we can discuss the substitution rule. So I'll leave this here for just a second longer in case anybody is still writing. But I think you'll agree that the calculations here aren't hard. You just take the derivative, and then you multiply that whole thing by dx. Maybe we'll do one more example where a variable is not x, just to make sure we're all comfy. Does anybody need more time on these? Okay, then I am going to move on. We'll do one more example. If u is equal to, let's say, t sine t, find du. Well, again, here's f. In this case, it's f of t. But the formula still works great. Du is going to be f primed of t times dt. So I need to differentiate this, which requires a product rule now. So I differentiate the t, leaving the sine t alone. And then I add that to what I get when I leave the t alone and differentiate the sine t. And then I slap on a dt. Okay, so here I needed a little product rule to calculate my differential. But it's still the same thing. You just take the derivative and then slap on a dt or dx or whatever your inner variable is there. That is, in this case, du. Any questions on calculating a differential? All right. We've seen these du's, dt's, and stuff like that showing up in our integrals, right? And the reason that we care about this now is because I'm going to want to make a change of variables in my integrals. We're going to talk about section 5.5, which is on the substitution rule. In integrals. The easiest way to think of this is the backwards chain rule. So I'll first write down the rule, and I want to use the exact notation that they use in the textbook. So hopefully you've taken some time to read this animal. Here's really the important stuff. I'll write it, the theorem, as they do here. So if you have an integral of a composite function, think about what this looks like. Forget about the integral and the dx for a minute. This kind of looks like I'm asking, looks like the output from a chain rule, right? If this was an f primed of g of x, then this would be exactly what you get from differentiating f of g. What the substitution rule says is that this is the same as doing the integral of f of u du, where u is equal to g of x, and thus du would be g primed of x dx. So this piece is du, and this is f of u. And this change of variables may seem trivial, but it's not. It's not just a relabeling of things. It's what we call a coordinate transform. You go from thinking about things on the x-axis, where x is your variable, to thinking about things on the u-axis, where u is your variable. This is the rule for an indefinite integral. There's a different rule for the definite integral. I'm going to get you comfy with this, then show you how to do the thing for definite integrals. So example. Maybe I want to evaluate the integral of sine of x squared times 2x dx. There's a bunch of shit going on here that's challenging. First, I have no idea what differentiates to the sine of x squared. That's complicated to find an antiderivative for. Sine of x, okay, I can find an antiderivative for sine of x. But sine of x squared, much harder. Also, there's multiplication between the 2x and the sine of x squared. I don't know how to anti-differentiate products. Remember in our last lecture, we talked about doing algebra to get rid of multiplication or division. So you just have like addition and subtraction in here, and then you can anti-differentiate each piece on its own.
Would it be negative cosine x squared?
We'll get there, but yes, yes it will. So the way we make this go is we choose to make the substitution. We choose to substitute u equals x squared, because I want to get rid of the x squared inside here. This is what's making life hard. If I'm going to substitute u equals x squared, I need to calculate du and rewrite my whole integral in terms of the variable u. Du here is 2x dx. That's the differential. When you do this, I recommend putting all this stuff in a little box. Under that substitution, the integral of sine x squared times 2x dx becomes, well, here I've got sine of x squared. X squared is u. So that piece will become sine of u. And 2x dx, that's exactly du. Du happens to be 2x dx. I could not make this substitution without this piece to soak up my du. Now, antiderivative of sine u du, I know how to do that. Who differentiates to sine? Negative cosine. So this is negative cosine of u plus c. And then you go back to your original variable. I asked for a question having to do with x's. So your answer needs to have to do with x's. The cosine of u is the cosine of x squared. So this is negative cosine of x squared plus c. Now, this is a very gentle example. You might even too, just by thinking about the chain rule, be able to answer the question, who has this as its derivative? Oh, cos of x squared. Yeah, that makes sense, because then you got a sine of x squared, and then by the chain rule, a 2x. But believe me when I say there are integrals that you can solve with substitution where you would never, ever see that without going through the step of rewriting it all in terms of this new variable. So what is substitution? It's where we choose to relabel parts of my integrand, like here, the x squared, as a new variable. And then you change the differential to be the differential of that new variable. So after you've picked your substitution, like here, I picked the substitution u equals x squared. You calculate the differential, du, and then you plug all that stuff in. And it just happened to be the case here, and it's by design, that this was exactly du, and that this was exactly sine of u. So I get instead the integral of sine u du, which I know how to do. Then you do the integral in terms of the new variable. You can only do that after getting rid of all the old variable stuff. If there were any x's floating around here, I'm fucked. Can't do it. Got to get rid of all the x's. Got to switch everything into the new variable. But then once you get there, like we did here, you can go ahead and do that integral and then go back to the old variable. Are you ready for a scarier looking example? Any questions on this one? All right, let's do it. Let's evaluate this horrific looking integral. E to the inverse tangent of t divided by 1 plus t squared dt. Holy shit, are we in trouble? Again, I have no idea what might have this as its derivative. And again, there's no sort of algebra I can do to clean this up. Everything is trapped inside the integral, so I can't start messing around algebraically with the whole thing. And then within the integral, there's no way to split this up. There's no way to rewrite this as addition or subtraction. I've got some crazy exponential, e to the inverse tangent of t, being divided by this irreducible polynomial. I'm in real trouble. But when we look at this thing, there are connections between the pieces that we can identify. You know that the derivative of the inverse tangent function is 1 over 1 plus t squared. The derivative of this is 1 over this. So first here, I would rewrite this. I would rewrite this as the integral of e to the inverse tangent of t times 1 over 1 plus t squared dt. That's the only algebra we can do here, right? Having something
would u be tan to the negative 1t?
Yes, that will be the substitution we make. All right, so now what I'm thinking is this piece is making the exponential look scary as hell. If this was just e to the x, I know how to integrate e to the x. And if I could also make this go away, boy, wouldn't that be nice. Well, this is the derivative of this. So if I substitute for this, then my differential will be this. So here I'm going to use a different variable just to get you guys in the habit of it. I'm going to choose to substitute z equals inverse tangent of t. So now dz is the derivative of inverse tangent t. That's 1 over 1 plus t squared times dt. And again, I recommend putting all this in a little box. So this shit right here is dz. And this shit right here is just e to the z. So my integral becomes, in terms of this new variable z, e to the z dz. Oh, and I know how to do that. That's not hard. E to the z, who has antiderivative e to the z? Well, e to the z plus any constant. And then your last step, so you make the substitution. You need to do this differential stuff. Without this, nothing makes sense. It's all out the window. You substitute for this piece. So this becomes e to the z. And this piece, very conveniently, happens to be exactly dz. So your integral becomes integral e to the z dz. I know how to do that integral. If I differentiate e to the z, I get e to the z. So this is e to the z plus c. And now I go back to my original variable. So that's e to the inverse tangent of t plus c. Neat, right? This is really a backwards chain rule. Right? That's what it is. If you were to differentiate this, you would need to do so using the chain rule. You would get e to the inverse tangent of t back, and then you would need to multiply by the derivative of the inverse tangent of t, which is 1 over 1 plus t squared. So the derivative of this is exactly this. And that's it. That means you did your integral correctly. These problems get challenging for two reasons. First, maybe it's not so obvious what you should choose to substitute. Second, maybe your differential isn't showing up exactly in your integral. Maybe you're off by a little bit. I want to address those two things, but first I want to make sure we're comfy with this example. Are there any questions about what we did in this example?
So when it's not exactly the differential, we have to do algebra until we get it.
Something like that. Yeah, it varies from case to case, but you'll need to algebraically manipulate your integrand until what you have here is at least containing what you have here, and then you can substitute in. So let's look at an example where things aren't exactly perfect. I want to integrate cos of pi x. If it was just cosine of x, I would say right away, oh, well, the antiderivative for cosine of x is sine of x. So, sine of x plus c. But it's not. It's cosine of pi times x. So do I have an inner function here that I could substitute for? Well, I could try substituting u equals pi x. That would get rid of the pi inside here. I just have cosine of u, which I know how to integrate, as long as the differential matches. But if you take the differential, du here is not just dx, it's pi times dx, right? Well, this is the same as saying that 1 over pi times du is equal to dx. So I can solve the differential relationship here for dx and then just plug that in. So in place of dx, I can write 1 over pi times du, and then everything will work out. So this would be cosine of u times 1 over pi du. Does everybody see that? In other words, I divided both sides here by pi to get dx alone. So I could get something I can plug in. Dx is 1 over pi times du. This dx is 1 over pi times du. And then the cos of pi x, that's just cos u. What can I do now? Suppose I handed you this problem written in this way. What would you do? Harris, that's a really good question in chat. Would this work on the same way on a function that uses the chain rule more than once? You can make several substitutions in a row. I can show you an example like that. That is possible for sure. And each step you do just like we're doing here. So now let's return to this. If I gave you this problem, suppose right now you're taking exam 3, and I gave you this problem, what would you do? Besides cry. Please don't cry. It's okay. It's not bad. This, I promise, is not bad. This is scarier than this. What sort of animal is 1 over pi? Is it an airplane? Is it, yeah, it's a constant multiple. This is 1 over pi times the integral of cos u du. And remember what we said, if this was only cos x, I know how to integrate regular old cosine. That's what I have here. The integral of regular old cosine is sine, right? Sine u differentiates to cos u. And so what I get here is 1 over pi times the sine of pi x plus c. You just have to go back to your original variable now. Or you could write this if you wanted as sine pi x over pi plus c. And in fact, this is an example of a family of problems that you'll want to get good at doing quickly. So like Andrew said, once I get to this step, I recognize that this 1 over pi is a constant multiple. It can come out. And then I'm just left with the integral of cosine u du, which is an integral I know how to handle. An antiderivative for cosine u is sine u. So the 1 over pi comes along for the ride, and I get 1 over pi times sine u plus a constant. And then you go back to the original variable. Lisa, you feeling a little better about this one? I want us to take our time here because not understanding substitution is one of these things that I see throw people off in Calc 2 right at the start. If you don't really internalize this, you're going to have a very rocky start to Calc 2. Let's try another sort of basic one where the differentials don't work exactly right, but we can still handle things. Suppose a is a constant. Evaluate the integral e to the ax dx. This has the same sort of issue as the last one, where inside, instead of just having x, I had pi x. Now inside, instead of just having x, I have ax. So what do you think we'll want to substitute for here?
AX.
Yeah. So I'll let z, I like to use the letter z for my substitutions. I'll let z be a times x. Now remember, a is a constant. So what is dz?
A dx.
Yeah, a dx, right? The derivative of a times x is just a. So this is a dx. Let me show you another way of thinking about this. Like in the last problem, I can solve for dx, right? Divide both sides by a. Another way to do this is within your integral, I could treat this as a over a times dx, right? I'm multiplying by a over a, or multiplying and dividing by a. This is the same as integral e to the ax times 1 over a times a dx. Notice I haven't plugged in any z's or dz's yet. Never mix your variables. I'll say this again, never, ever, ever mix around variables in an integral. Just don't do it. Don't do it, don't do it, don't do it ever. Okay. This piece is dz. So now I have e to the ax, that's e to the z, times 1 over a, that's a constant, times a dx. A dx is dz. So notice in all of these lines, the only variable is x. In this line, the only variable is z. I will never mix the a's or the x's and the z's. Shouldn't do it. Don't do it. Those objects don't make sense. And now, just like in the last problem, the constant can come out. You've got 1 over a that can come out, and what's left is e to the z times dz. An antiderivative for e to the z is e to the z. So you get 1 over a times e to the z plus c. And then you just go back to your original variables. So this is 1 over a times e to the ax plus c. This is how we solve these problems. The truth is, shit can be a lot worse. If your differential is a constant times dx, then you can always make those substitutions go through by using this trick or the method I showed you in the last problem where you solve for dx and plug in. Daniel, I differentiated ax. So here, ax primed is just a. So this has this as its derivative. And then I just slap on the dx. Okay. That's the funny part. Yeah, where did the a over a come from? Well, I knew I needed an a that I could group with dx, right? If we look here, I don't have this. I just have this. In order to change my variable into z, I need to change my dx's into dz's. But dz isn't equal to dx, it's equal to a times dx. And I don't have an a that I can group with this dx right now. But if I multiply by a over a, then I can take this a from the upstairs and group it with the dx. So I chose to multiply by 1 in the form a over a, because that allowed me to take the a from the numerator and group it with the dx, and then the a from the denominator is just a part of this constant, 1 over a, and I'm not afraid of constants because they will pop out. But I needed to make this show up somehow, because this is dz. So I needed to make a dx show up somewhere in my integral. And one way to do that is to multiply and divide by a, then group the a from the numerator with the dx. I think most people don't like this method as much as the previous one. You want to see this solved the way we did the other one? The way we handled this same problem with the sine pi x integral last time was, once I got to this stage, I said, okay, this means that 1 over a times dz is equal to dx. So everywhere there's a dx, I just plug this in instead. So I'll have e to the ax, that's e to the z, times dx, that's 1 over a times dz. And then just like before, I shuffle my 1 over a out front to get this, which is this, which is this. So same thing, just kind of two different ways of thinking about it. You can solve for the dx and then plug in, which will get you to the same place. Or you can multiply and divide as needed to make your a dx show up, and then just replace that by dz. Compare these two, right? Compare this to this, or this to this. You get the same thing. It's just two different ways of doing the algebra. This way of thinking about things will generalize better. This way of thinking about things is usually easier when you're first starting out. Okay, other questions here? Okay, let's try something a little harder still. One of the problems you'll encounter from time to time is that you want to make a substitution that looks like it'll work well for part of the problem, but doesn't do everything. Now here, this is, I'm going to tell you right now, this is not an integral we're going to be able to solve. But I want to see what happens if we make the substitution z equals natural log of x. Because I've got a natural log of x inside here, I'd like to get rid of that inner function. First, let's rewrite this integral. That's sine of natural log of x times x squared plus 1 times 1 over x dx. No calculus yet, just rewriting the inside. If I now try to sub z equals natural log of x, then dz would be 1 over x dx. Do we all agree on that? So this piece would be the sine of z. This piece would be dz. But what about this piece? Remember, I cannot mix variables. I'm not allowed to have x's and z's in the same integral. Just not allowed. So how can I write x squared plus 1 in terms of the variable z? If z was just equal to x, then x squared plus 1 would be z squared plus 1, and I could just plug in a z there. But z isn't equal to x. Z is equal to the natural log of x. We can solve for x. We can solve our substitution. For x. If z is equal to ln x, that's the same as saying e to the z is equal to x. Now, x squared plus 1 must be e to the z squared plus 1, which is e to the 2z plus 1. So our integral would become integral sine of z times e to the 2z plus 1 times dz. That is what happens when we make this substitution. This is the transformed integral. You see, every piece has been replaced by his equivalent piece in terms of z. I'll show you how to do this integral in Calc 2, but this is a little bit beyond us from here. The substitution step, though, is not beyond us. The next move here in Calc 2 would be to run the backwards product rule, which is called integration by parts. And again, you won't learn that until a few weeks into Calc 2. But it's important that you see how to go from the original integral to here. Are there any questions about this step here where I just rewrote the integral? Forget about labeling things. Just going from this form to this form, the algebra. Does everybody see where the 1 over x here came from? That's the x downstairs here. The x squared plus 1 just chilling. Then since I'm substituting z equals ln x, the sine of ln x would just become the sine of z. the 1 over x dx just becomes dz. It's this piece in the middle which is hard. And the trick was to go back to your substitution and solve for the original variable. So here, I'm just solving this equation for x. You do that by exponentiating on both sides. You get e to the z equals e to the ln x. E to the ln x is just x. Okay. I want to show you one slightly simpler example of something like this where we can follow up and finish the integral. Let's evaluate the integral x times, let's see, the square root of x minus 1 dx. Quick question. Is this equal to the integral of x times the square root of x minus the square root of 1? Can I do this? Hell no, right? Square roots don't do that. The square root doesn't play nice with addition or subtraction. Cannot do that, cannot do anything like that, can't do that shit ever. You'd be surprised how often I see it, even out of Calc 2 students, so internalize that. Yeah, I wish they did all the time. That would make life so much easier. But I can't do that. Any ideas what we could do? Well, that's what we're saying, is we can't distribute the x because I can't do this. If I could do this, then I could distribute the x. I'm sorry, Harris, what was it?
Could you put x minus 1 to the 1/2 power?
We could, but that doesn't really get me anywhere. This is true. It is true that this is equal to x times x minus 1 to the 1/2 dx, but this power doesn't distribute. And in my order of operations, powers takes precedence over multiplication. So I can't distribute this x in here either. So sort of for the same reason why I can't do this, I couldn't distribute this over these because the power takes precedence. Yeah, Andrew's got it. If I substitute u equals x minus 1, then this, so I'm going to actually scribble this. It's not that it's wrong, it's just not useful. If I substitute u equals x minus 1, then this will become the square root of u, which is easier to deal with because there's no subtraction or addition underneath the square root. What is du? It's 1 times dx, right? Or just dx. So if I make that substitution, then I'll have the square root of u. Dx is the same as du. But what should I put here? It can't just be an x because I can't mix the x's and the u's.
U plus 1.
Good. Solve u equals x minus 1 for x. That's the same as saying x equals u plus 1. So this would be integral u plus 1 times the square root of u du. Why is this nicer? Because now I can distribute. Now the addition is out here instead of having it under the square root. So from here we would distribute. This is u times the square root of u plus 1 times the square root of u du. And again, we're putting our whole integrand in parentheses here because it is separated by some addition and subtraction. U times the square root of u is u to the 3/2, and 1 times the square root of u is u to the 1/2. And now we can use our power rule. If you add 1 to 3/2, that's 5/2. If you add 1 to 1/2, that's 3/2. Slap on your plus c. Dividing by 5/2 is the same as multiplying by 2/5. Similarly, the 2/3. And then your last step is to go back to your original variable. U is x minus 1. So this would be 2/5 times x minus 1 to the 5/2 plus 2/3 times x minus 1 to the 3/2 plus a constant. And you can verify that this is not the same thing you would get if you did that illegal algebra at the start. That illegal algebra at the start is not only not kosher, but it will give you a wrong answer. It's not one of those like, you can hack and pretend like this is okay because it works out at the end things. It doesn't. This is a neat trick. You try to do a substitution, but not everything lines up right away. So you go back to your substitution and you solve it for the original variable. And then any instances of that variable that are still floating around in your integral, like here where we had an x, you can replace by your new variable. X was u plus 1. Okay. If there are any x's left over, I just write them as u plus 1. So these are the two challenges in substituting. Maybe there's some variable stuff in your original integral that doesn't fit nicely into the substitution. That's what happened here. And you have to go back and solve your substitution for the original variable. And then any instances of that original variable still floating around, you just plug in. You plug in whatever you got when you solved. The other and kind of larger challenge is what to do if your differential doesn't line up exactly with what you have. And that's the problem that we saw in the previous guy, or the two before that, right? The e to the ax integral and sine pi x integral. I want to look at one more where the differential appears a little bit off. And I'd like it to be more challenging than these. These are all just such simple examples. Let's do this. Yeah, x over the square root of 1 minus 4x squared. Here again, I've got some stuff underneath the square root that's separated by addition or subtraction. Fuck, I hate those things. I want to make this go away. I want to make this subtraction go away more than anything else. So I want to substitute for everything under the radical. That's a pretty common move. If your integral has some radicals with some variable stuff underneath, especially if that variable stuff is separated by addition or subtraction under the radical, substituting for the radicand, the stuff inside, is a very common move. So here I'll try to substitute u equals 1 minus 4x squared. That way this just becomes a square root of u. Du then, the 1 differentiates to 0, negative 4x squared differentiates to negative 8x. So I have negative 8x dx. I can rewrite my original integral as integral 1 over the square root of 1 minus 4x squared times x dx. But again, the challenge here is that this is not exactly this. It's off by a little bit. It's off by a factor of negative 8. So what I would do, and what I encourage you to do, you have an x dx to spare that you would like to get rid of. You know that du is negative 8 times x dx. So divide both sides by negative 8. That leaves you over here with the x dx, which is exactly what you're trying to replace. And it tells you what it is in terms of du. So this would be integral 1 over the square root of u, 1 minus 4x squared is u, times negative 1/8 du. And you need to remember this is multiplication. So this is negative 1/8 du, like that. That negative 1/8 is a constant multiple. It can come out, and you get integral 1 over square root of u du, which is negative 1/8 integral u to the negative 1/2 du, which you can now use your power rule on. The negative 1/8 comes along for the ride. U to the negative 1/2 anti-differentiates to u to the positive 1/2 divided by positive 1/2 plus c, which is the same as negative 1/4 u to the 1/2 plus c. This divide by 1/2 is the same as multiply by 2. 2 times negative 1/8 is negative 1/4. So that would be negative 1/4 1 minus 4x squared, all to the 1/2 plus c. And remember, you cannot distribute this power over this subtraction. So that's as nice as it gets. You can write it as negative 1/4 square root 1 minus 4x squared if you want to, but you don't have to. I would accept either of these as final answers. Not this, but either of these is okay. Questions on this example? Okay, then I have good news for you. There's 2 new integrals that we need to be able to do that we haven't been able to do that we can now do. And there's lots more. But there's 2 kind of fundamental ones. Yeah, it's really not too bad. If you think about it carefully, it's not too bad. Tangent, the integral of tangent. I told you guys what it was a while ago. Does anybody remember? It involved a natural log. The way you do this is first rewrite it as integral sine x over cos x dx, right? Because tangent is sine over cosine. And then you substitute for the bottom. If u is cos x, then du is negative sine x dx. So I think of this as integral 1 over cos x times sine x dx. And I see that this piece is negative du. And this piece is 1 over u. So this will become integral 1 over u times negative du. And the negative can come out front. And an antiderivative for 1 over u is the natural log of the absolute value of u plus a constant. So you get negative natural log absolute value cos x plus c. That is the integral of tangent. The other kind of exciting one, integral of cotangent, goes the same way. It's actually easier. And I invite you to try it. Sure. If you're feeling fancy, you can actually bring this negative inside as a power. The negative first power of cosine, 1 over cosine, is secant. So some people prefer to remember it like this, because tangent and secant are kind of connected. Again, either of these last two is fine. I usually think about it like this, but I know some people prefer to remember it like that. Cotangent, again, very, very similar. You'd start by rewriting cotangent as cosine over sine, then substitute for the bottom. I'm going to move on to this last one. This will be the last example. Rather than talking about definite integrals today, I want to show you one more example of an indefinite integral. And this one is a doozy. So we'll be moving to the next page in about 5, 4, 3, 2. Last example for today. Integral of secant. What you'll see when you take Calc 2 is that integrating odd powers of the secant function, challenging, very challenging, fun, but not easy. I'm going to do something here that at a glance makes no fucking sense. I'm going to multiply by secant x plus tangent x over secant x plus tangent x. And I'll just ask you to trust me for a second. So I'll leave this alone, and then I'm going to multiply by secant x plus tangent x over secant x plus tangent x. I just multiplied by 1, right? Secant plus tangent over secant plus tangent, that's 1. So in the same way that multiplying by a over a is fine, multiplying by 2 over 2 is fine, multiplying by this is fine. It's mighty weird, I'll admit that. Nobody would think to do this for sure. Until somebody did think to do it. And then they noticed that if you distribute this, something very cool happens. So remember, this is secant x over 1. I'll multiply those two fractions straight across. Upstairs, I need to distribute secant times secant, secant times tangent. Secant times secant is secant squared. Secant times tangent is, well, just secant times tangent. And the bottom is 1 times secant plus tangent. So that's just secant x plus tangent x. There's only one reason I would introduce this today, and that's because today is the day where we learn about substitution. So you can guess that the move is going to be a substitution. Does anybody see a connection between any of these pieces and their derivative here? What's the derivative of secant?
Secant tangent.
Yeah, the derivative of secant is secant tangent. And the derivative of tangent?
Secant squared.
Secant squared. Okay. Well, let me rewrite this then as 1 over, I'll change the order of addition downstairs. That's always allowed. 2 plus 5 is the same as 5 plus 2. Secant plus tangent is the same as tangent plus secant. And then I'll rewrite the top over here as secant squared plus secant x tangent x. And there's your dx. All right. So this, purely through algebra, is equal to this. It's weird algebra. It's not something anybody would normally think to do, but it's true. And now the derivative of this is sitting right here. So what do you think the move is?
Z equal to tan x plus secant x.
Very good. So if we make the substitution, z equals tangent x plus secant x, then dz will be secant squared x plus secant x tangent x all times dx. And remember those parentheses I talked about earlier, they're important here. This piece is dz. This piece is 1 over z. And I know how to integrate 1 over z dz, don't I? So here's my substitution. Put everything in a box. It makes it easier to see what came from where. Integral 1 over z is the natural log of the absolute value of z plus a constant. So that's the natural log of the absolute value. Usually people write the secant first. That, my friends, is the integral of secant. natural log of secant plus tangent. Mighty strange. It's just how it works out. There is a beautiful connection here between trig functions and the natural log that you may be starting to smell a little bit. The integral of tangent involving a natural log, the integral of secant involving a natural log. A brilliant man several hundred years ago, I want to say around the time of the American Revolution, discovered the exact relationship between trig functions and natural logs. His name was Leonard Euler, famous for also being the namesake of the number E. Right? The number E is called E because it's Euler's number. And he actually discovered, by playing around with things like this, an amazing connection between complex numbers, exponentials, and trig functions called Euler's formula, which again, I'll prove for you towards the end of Calc 2. But for now, I just want to introduce the idea. Some neat connection between trig functions and the natural log exists. This is all I have for you guys today. I will give you the formula and techniques for integrating definite integrals by substitution on Wednesday. So Wednesday is another very important class. Yep, normal office hours today and tomorrow. I do teach Calc 2. Yep, Calc 2 is kind of my baby. It's that's the class that Santa Fe kind of lets me take care of. So every semester I have at least one Calc 2. I think I have one or two of them next semester. I'm not sure if they're full yet. Oh shit. No, don't stress. Nurses, believe it or not, nurses need to take some calculus also. I think most nursing programs require at least Calc 1. That is all I have for you guys today. So if you would like to chat a little bit more, you can come see me in office hours, or otherwise I'll see you guys on Wednesday. But that is it. I hope you guys have a lovely rest of your day. Take a look. I'm going to be popping open a new homework. You should get started on them. Do all the ones with the indefinite integrals first, and then on Wednesday I'll show you how to do the definite integrals. Okay? All right. Take care, guys.